Now we come to the case when let us now suppose that rank of L is precisely D. This means that determinant of L, well, first it means that L is invertible, and it also is equivalent to saying that determinant of L is not equal to 0. Now L is a linear transformation. Since L is a linear transformation, for any x, y in Rd, we have the following inequality, which is that L of x minus y equals to Lx minus Ly, and this is less than or equal to some constant times x minus y. So there exists a positive constant c such that, well, non-negative constant c such that you have that the norm of L of x minus y is less than or equal to this constant c times the norm of x minus y, which means that L is Lipschitz. So if you recall what is a Lipschitz function, this is exactly the definition for a Lipschitz mapping, and L is Lipschitz means also that it is a continuous map. So L is, in our case, it is a continuous bijection, which implies that L is a homeomorphism of Rd. So now that we have seen that L is a homeomorphism when rank of L is D, then we can say that if U is open, this implies that Lu is open, and so it's measurable in particular. So measurable, and if F is closed, this implies that Lf is closed, and so measurable. So in the particular case when you have open and closed sets, we have proved that the image Lu and Lf are open and closed respectively, and therefore both are measurable. Now observe that Lf is a subset of Le is a subset of Lu whenever F is a subset of E is a subset of U, and if U is open and F is closed, then this is closed and this is open. So let me write Lu is open and Lf is closed, as we have seen. So if for epsilon greater than 0 we have a closed subset F and an open subset U such that measure of U minus F is less than or equal to epsilon, it suffices to show that the measure of Lu minus Lf is also less than or equal to epsilon. So note that m of Lu minus Lf is equal to measure of L of U minus F, because L is invertible, so it preserves intersections, and so therefore we can write this, and this is an open set, so it suffices to show that m of Lv is precisely the modulus of the determinant of L times M of V for any open set V. So this would imply that the measure of Lu minus F is less than or equal to, or rather is equal to, modulus of the determinant of L times the measure of U minus F, and this is less than or equal to determinant of L times epsilon. And so we will have shown that LE is Lebesgue measurable. So we will prove that for any open set we have this formula that M of LV is equal to modulus of determinant of L times M of V. In fact, we are going to show something even stronger, which is that if we will show that if E belongs to the Lebesgue measurable set and LE belongs to the Lebesgue measurable set, then we have measure of LE is equal to determinant of L modulus of the determinant times ME. So how do we show this? So note that if measure is finite, measure of E is finite, then given epsilon greater than 0, there exists a collection Bi I equal to 1 to infinity of boxes in Rd such that the sum I equal to 1 to infinity MBI is less than or equal to ME plus epsilon. So this is basically the first definition of the outer measure that we used, which is the covering, which used the covering of E with boxes and estimating it by taking an infimum. So we have this. Now LE is then covered. So first of all, here E is covered by these boxes. So LE is covered by the union of these boxes LBI. So this implies that the outer measure of LE, which is the same as the measure because again LE is assumed to be Lebesgue measurable. So this is less than or equal to the sum MLBI, I equal to 1 to infinity, and this we know is equal to modulus of the determinant times MBI. For each I we have this equality, which is measure of LBI is equal to modulus determinant L times measure of BI, because we know this for elementary subsets. And so we get modulus of determinant L measure of E plus epsilon. So this implies that measure of LE is less than or equal to modulus of the determinant of L times measure of E. Now I am going to reverse the roles of LE and E. So let E prime be LE and L prime be L inverse. Then the measure of L prime E prime is less than or equal to determinant of modulus of the determinant of L prime times the measure of E prime. But this is nothing but measure of E. Left hand side is simply E. L prime E prime is simply E, and this is determinant of L inverse and the right hand side is m of LE. So this implies that m of LE is also greater than or equal to determinant of L times measure of E. And so this implies that MLE equals determinant of L modulus times ME, when our assumptions were that first of all that E belongs to LD, LRD, LE belongs to LRD, and measure of E is finite. So if we drop, now we are going to drop this condition that measure of E is finite. So if measure of E is infinite, we can write measure of we can write E as a countable union n equal to 1 to infinity E intersection AN, where AN is the set of points in RD such that the norm of x is greater than or equal to n and is strictly less than n plus 1. So this becomes a disjoint union, and so measure of E is equal to the sum of these E intersection ANs n equal to 1 to infinity, which implies that the measure of LE is equal to the sum LE intersection AN, and each of these is now can be written E intersection AN n equal to 1 to infinity. This is modulus of the determinant times ME intersection AN n equal to 1 to infinity, and this is nothing but modulus of the determinant times ME, and the left hand side was measure of LE. So also when measure of E is infinite, we have this equality. So this proves in particular that when E is an open set, is open, then measure of LU is equal to modulus of the determinant of L times measure of U, and this is what we wanted, because here this is precisely what we wanted to show, that for any arbitrary set the measure of LV is equal to determinant of L modulus times M of V, which showed that LE is Lebesgue measurable. And now that we know that LE is Lebesgue measurable, then we can again go back to our to something that we just proved, that if E is Lebesgue measurable and LE is Lebesgue measurable, then we can write this formula. So basically we are now done with the whole proof. This completes the proof. The proof of the second part. So we have seen that our Lebesgue measure satisfies our geometric intuitions, which is finite, additivity, and invariance under translations, rotations, and reflections. So now is a good time to see an example of a non-measurable set, a set which is not Lebesgue measurable, and how this finite additivity property fails for such sets. So for this, note that this is called the construction of a Vitali set. So this Vitali set is going to be is not going to be Lebesgue measurable. So first note that the set of rational numbers, this is a additive subgroup of the real numbers, additive subgroup of R. So we can partition R into cosets, which we write as the set of cosets is x plus q, such that x is in R. So the quotient quotient group is given by R mod q, and this is simply the cosets, right cosets or left cosets of the rationals given by x plus q. So now each coset C in R mod q is dense in R. So C intersection, the interval 0, 1 is non-empty for any coset C in R mod q. So now I am going to use the axiom of choice again to construct this Vitali set. So axiom of choice implies that there exists a set which I call V, which contains exactly one element of C intersection 0, 1 for each coset C in R mod q. So we have constructed a set which for each coset C picks out a number in C intersection 0, 1, and this V is precisely made up of such elements, picking up one from each coset C which lies in the interval 0, 1. So V is the set of numbers x in the interval 0, 1 such that x belongs to C intersection 0, 1 for exactly one coset C of R mod q. So this is called the Vitali set, and the theorem is that V is not Lebesgue measurable. So let's try to prove this. So first observe that we can write two things. First is that V is a subset of 0, 1 by construction, and given any x in 0, 1, there exists a rational number q in say -1, 1 such that x minus q belongs to V. So this is by the construction of the Vitali set, because we are choosing only one number from each coset C intersection 0, 1. So for any given x, there exists a rational number q such that x minus q belongs to V. This is because x belongs to 0, 1 implies that x belongs to C for some coset C, because this is a partitioning of R into cosets. So in particular, for x a real number between 0 and 1, it belongs to some coset. It must belong to some coset C, and choosing the representative from the Vitali set, this implies that X belongs to so let me here write XC for the representative inside the Vitali set for the coset C. So this means that X equals XC plus some rational number Q, and because both X and XC belong to 0, 1, this is in fact a rational in -1, 1. So this is why we get a rational number Q such that X minus Q belongs to V. On the other hand, if Q is not equal to Q prime for rationals Q and Q prime in -1, 1, then V plus Q intersection V plus Q prime is empty. These two are disjoint subsets of -1, 1. So this is because if X belongs to V plus Q intersection V plus Q prime, so X can be written as XC plus Q for some coset C in R mod Q, and it's also equal to XC prime plus Q prime for some coset C prime in R mod Q. So this implies that XC is equal to XC prime plus Q prime minus Q, but this is again a rational number, and which means that C must be equal to C prime, and this means that XC and XC prime are two representatives from the same coset, which is not allowed. This implies that XC and XC prime with XC not equal to XC prime are now two representatives from the same coset C belonging to 0, 1. So XC and XC prime both belong to 0, 1, and this is not allowed, which is a contradiction. So we see that we have, whenever Q is not equal to Q prime, these two translates V plus Q and V plus Q prime are disjoint. Now note that the union V plus Q, when Q ranges in the rationals between -1 and 1, this is a subset of -1, 2, the interval -1, 2. So this implies that the measure of this union, this is a countable union because it's a union over rationals in -1, 1. So this measure is bounded above by 3, and also we have that this is a countable union of disjoint sets. So we have this sum over the rationals in -1, 1 mv plus q. So I should rather write m star instead of m, because we still don't know whether any of these subsets are Lebesgue measurable. So if V is assumed to be Lebesgue measurable, then of course m star V plus q. So V plus q is measurable, V plus q is measurable for all q in -1, 1 intersection q, and the measure of v plus q, now I am removing star because it is a Lebesgue measure, is the same as the measure of v. So we have that the sum minus 1 1 mv is less than or equal to 3, which implies that the measure of v must be equal to 0, because if it is positive then it is going to be infinite. But here we have a bound of 3 on this whole thing, on this infinite sum. So mv must be 0. On the other hand, we have that 0 1 is contained inside this union q in minus 1 1 v plus q. This is because of due to property 1 above, and this is a disjoint collection due to property 2 above. So this means that 1 is less than or equal to the measure of this set v plus, this is the union of v plus q's. On the other hand, this was the sum of these things, measure of v plus q, but it was v was assumed to be Lebesgue measurable, so it is measure of v, and this is 0 because if v was assumed to be Lebesgue measurable, then mv must be 0. So this is a contradiction, which is a contradiction. So v is not Lebesgue measurable. So this is the construction of the Vitali non-Lebesgue measurable set, and now I am going to show that this v fails the finite additivity property. So we will prove that this following lemma, that if E is a subset of RD, rather 0 1 such that the outer measure of E plus the outer measure of 0 1 minus E is equal to 1, then E is Lebesgue measurable. So as an immediate corollary of this lemma, assuming that this lemma holds, as an immediate corollary of this lemma, we have that for the Vitali set 0 1 minus v is not equal to 1. Just as a remark, note that this complement 0 1 minus v is also not Lebesgue measurable, because Lebesgue measurability is closed under complements. So if this was Lebesgue measurable, if you take the complement, then you will get v, which would then be Lebesgue measurable, and so we have a contradiction. So if v is not Lebesgue measurable, the complement inside 0 1 of v is also not Lebesgue measurable. So let's now prove the lemma. So proof of lemma. So let's fix epsilon greater than 0, and we choose open sets U which cover E and V which covers 0 1 minus E, such that m star u, or rather mu, is less than or equal to m star E plus epsilon, and mv is less than or equal to m star 0 1 minus E plus epsilon. So let me take epsilon by 2 so that our analysis will be a little bit easier later on. So this implies that the measure of the union of these two sets U and V is less than or equal to mu plus mv, which is less than or equal to m star E plus epsilon by 2 plus m star 0 1 minus E plus epsilon by 2, but these two give you the sum 1 and these two give you the sum epsilon. So in total it's 1 over 1 plus epsilon. So the measure of the union of U and V is bounded above by 1 plus epsilon. On the other hand, the measure of U intersection V, which is equal to mu plus mv minus mu union V, and this is less than or equal to 1 plus epsilon. So this first term is less than or equal to 1 plus epsilon, and the second term is greater than or equal to 1, because since note that since, let me write it here, since 0 1 is a subset of U union V, so the measure of U union V is in fact greater than or equal to 1. So this is less than or equal to epsilon. So the intersection has bound, upper bound epsilon. In turn, this means that the measure of U union V minus this interval 0 1, which is equal to measure of union of U and V minus measure of 0 1. This is of course 1, and this was bounded above by 1 plus epsilon minus 1. So this is again bounded above by epsilon. So now if you take U minus E, then this is let me first write that U minus E. So you can write this as U intersection E complement, which can be further written as U intersection E complement intersection 0 1 union with U intersection E complement intersection 0 1 complement. So the first one, this is nothing but U intersection 0 1 minus E, and the second one is nothing but U intersection 0 1 complement. This is because since E is a subset of 0 1, so 0 1 complement is a subset of E complement, and so the intersection is simply the smaller set 0 1 complement. So now this is a subset of U intersection V, because V is an open set that covered 0 1 minus E, and the second one is a subset of U union V minus 0 1. Now we have control over the measures of both these sets, so we can immediately get that the measure of U minus E is less than or equal to the measure of U intersection V plus the measure of U union V minus 0 1. So both are equal to less than or equal to epsilon, so this is equal to 2 epsilon, and so E is Lebesgue measurable. So this finishes the proof that finite additivity property does not hold for this Vitali set, because if there was equality, then we should have been Lebesgue measurable, which we have seen that it's not the case. So we have seen that for non-measurable sets, finite additivity fails to hold.